In this task, I've built an aged care bed monitoring system on the Arduino Nano 33 IoT using FreeRTOS. The system has four hardware components: a DHT22 temperature sensor for patient's body temperature, an FSR pressure mat to detect whether the bed is occupied, a red LED for local visual alarms at the bedside, and a Python nurse dashboard connected over USB. Rather than using a single blocking loop, the program is structured as 5 separate FreeRTOS tasks, each owning one monitoring responsibility. I will walk you through the hardware setup, the task design, the low-level register code, and then demonstrate all features live. Here is the hardware wiring. The DHT22 temperature sensor data line connects to digital pin D2 on the Nano 33 IoT, which is PB10 on the SIT329 microcontroller. My DHT22 Dakin class drives this pin using direct port register access. PMUXEN is cleared so the pin is not routed to any peripheral multiplexer. The pull enable is set to enable the internal pull-up resistor that keeps the data line high between readings. The FSR force-sensitive resistor is wired as a voltage divider into analog pin A1, which maps to PB02 and ADC channel 10. ADC Dakin reads this value using the SAMD21 ADC hardware registers configured for 12-bit resolution, giving values between 0 and 4095. The red alarm LED uses the Nano's built-in LED on digital pin D13, which is PA17. GPIO Dakin writes the outset and out clear registers directly to turn it on and off without any Arduino API calls. Finally, the USB port carries JSON telemetry between the MCU and the Python GUI running on the nurse computer. This slide shows the 5 FreeRTOS tasks and how their priorities were chosen based on safety criticality. Tap detection task has the highest priority because it handles a direct patient emergency. When a patient taps the FSR mat 5 times within 2 seconds, the help alarm must be raised immediately and cannot be delayed by any lower priority work. Its deadline is classified as hard, meaning a missed response has immediately safety consequences that cannot be corrected after the fact. LED alarm task is the second highest priority, because if the LED fails to blink during a fever state, the nurse receives no visual warning at the bedside. That is also a hard deadline. Temperature task and pressure tasks are both medium priority with soft deadlines. Body temperature and bed occupancy are both slowly changing physical variables, so a reading that arrives a few seconds late has no meaningful clinical effects. Both tasks use V-task delay until for drift-free periodic scheduling. Communication task is the lowest priority, also with a soft deadline. A 1 or 2 second delay in the GUI has no safety consequences. The shared system state structure is protected by a FreeRTOS mutex with priority inheritance. If communication task holds a lock when tap detection task needed, the scheduler temporarily boosts communication task priority so it releases the lock as quickly as possible. This slide shows the register level initialization inside the two custom sensor classes, which replace Arduino API calls with direct SIT329 peripheral access. In SIT22 they can begin. I first call getPort group to obtain a pointer to the SIMD21 port group structure for the chosen port letter. I then calculate the pin mask by shifting one left by the pin number. PMUXEN is cleared to prevent the pin from being routed to any peripheral multiplexer, keeping it as a plain GPIO pin. Pull enable is set to enable the internal pull-up resistor, which holds the data line high between sensor readings. Release line then sets the pin direction as an input ready to receive data. In ADC, they can set up ADC. The first step is to gate the ADC clock domain through the PM APBC mask register. The 48 MHz generic clock 0 is then routed to the ADC peripheral via the G clock control register. The prescaler is set to divide by 64, which gives a 750 kHz ADC sample clock, and the resolution is set to 12 bits, so the FSR voltage divider produces results between 0 and 4095. This slide explains the temperature monitoring task. Temperature task runs every 5 minutes in deployment. For this video demonstration, I've set demo timing to 1 in the sketch, which shortens the period to 5 seconds so the features can be shown quickly. At each interval, if the demo override is not active, the task called DHT22 read temperature. That function drives the PB10 data line with direct port register operations to send the 2 millisecond start pulse and then read back the 40 bits DHT22 data frame. If the frame is valid and the checksum passes, the temperature value is passed to set temperature state, which updates system state temperature alarm to one of 3 levels. Below 38 degrees Celsius is the normal state, and the LED state off. Between 38 and 39 degrees is the fever blink state, where LED alarm task toggles the LED every 500 milliseconds for a 1 Hz blink rate. Above 39 degrees or below 35 degrees is the critical state, where the LED stays on steady and the GUI shows a critical alarm. If the DHT22 read fails, the diagnostic error code is stored in system state and displayed in the GUI. This slide explains how the FSR sensors serve two separate purposes, handled by two different tasks running at very different rates. Pressure task reads the ADC channel every minute. If the raw value is 900 or above, the bed is classified as occupied. That first hole was chosen to correspond to the sustained weight of a person lying on the mat. The result is stored in system state and forwarded to the GUI by communication task. Tap detection task runs entirely independently at a much faster rate of 20 milliseconds. It looks for rising pressure transition, meaning it counts a tap each time the FSR goes from unpressed to pressed. A sustained press counts as only one tap, so the patient cannot accidentally accumulate taps by holding the mat down. If 5 distinct rising transitions occur within a 2 seconds window, set help alarm is coded with true, which sets the help alarm flag in system state and causes LED alarm task to light the LED. When the nurse clicks reset but alarm in the Python GUI, a single character out is sent over serial. The MCU reads this in communication task and passes it to handle GUI command, which calls set help alarm with force to clear the flag. This slide shows the serial communication protocol between the MCU and the Python GUI. Communication task sends one complete JSON object per second over the USB serial link. Before serializing, it takes a snapshot copy of the system state structure protected by the mutex, then releases the mutex before any serial output begins. This is important because a serial write can take several milliseconds, and holding the mutex during that time would unnecessarily block higher priority tasks. The JSON carries the temperature readings, the raw FSR ADC value, the bed occupancy flag, the temperature alarm state, the help alarm flag, the SIT329 read status, a diagnostic error code, the temperature mode indicator. On the Python side, the GUI passes each JSON lines as it arrives, updates all its dashboard fields in real time, and appends a timestamped row to hklog.csv. This satisfies the continuous data logging requirement from the task sheet. The GUI also sends single character commands back to the MCU. The character out clears the help alarm. The characters 0, 1, and 2 sets normal, viva, and critical demo temperature overrides respectively. The character D switches back to reading the actual DHT22 sensor. Now, I will run through the demonstration in sequence. First, I will run the Python GUI. Select the Arduino COM port from the drop-down and click Connect. All 8 JSON fields should start updating immediately. Second, I will click the Viva Demo button and show that the physical LED on the board starts blinking at approximately 1 Hz. Then I will click Critical and show the LED switching to steady on. Then I will click Normal to return to the base state. Third, I will press the FSR mat firmly and release it, and you will see the bed occupied indicator toggled in the GUI. Fourth, I will tap the FSR map quickly 5 times within 2 seconds. The GUI should show help required in the help alarm field. Fifth, I will click Reset Alarm in the GUI, and the help alarm should clear, showing the nurse reset function works end-to-end. Note that the demo timing is set to 1 in the sketch for this recording, which uses 5 seconds temperature period and 3 seconds pressure period instead of the deployed 5 minutes and 1 minute intervals. Thank you.